Let's take another look at our very nice theorem 3. When I saw this for the first time, I found it very surprising because condition 1, invertibility of A, was kind of our minimal assumption before we even started this whole idea of approximating the equation. But then it turns out that property 2, which is where we want to go, is already equivalent to our minimal assumption A. So it seems that this uniform convergence gives you a very strong binding, a very strong relationship between your operators an that approximate A and the limit A itself. Let's just quickly remind ourselves that property 2 is what we call applicability. And then, property 3 turns out to be just the same. It's applicability in disguise. Okay, and of course also property 4 is the same, but it already looks quite different. So it's applicability so much in disguise that it already deserves its own name. And the name for property 4 is going to be stability. So here it is, the missing word from the title of our course. So let's quickly write this down as a definition before we forget. So we say that an operator sequence AN is stable. And here comes property 4. So if there exists an integer n0 such that starting from this integer, the operators from our sequence are invertible and the sequence of inverses is bounded. Okay, and of course you can talk about the inverses only if n is n0 or bigger. And if you want, we can express that boundedness condition also explicitly. So you could say that there's a uniform upper bound on the norms of your inverses. Or you just abbreviate that as follows. The supremum of your norms of inverses, which is the best upper bound that you can find, is a finite number. So if you want to draw something here, then this would probably be the following graph, where this is your n-axis, where your index is running, and this is where you put your norm of the inverse. And if an operator is not invertible, then we sometimes say its inverse is just infinitely large. So we could say that infinity is the end of that axis, and that for cases less than n0, so if n is less than n0, then sometimes an might not be invertible. So our plot is assuming infinity, maybe sometimes, not all the time when n is less than n0, but maybe a couple of times. In the other cases, it's something finite, who knows. But the key is that once you've reached this point n0, then you will not see infinity anymore, just finite stuff. And moreover, that finite stuff is limited from above by some number that we denoted as capital N here. And if you want, then you could even abbreviate the whole definition by the following expression. The lim sup of the norms of our inverses is finite. So, well, of course, if you give me that answer in the exam, then you have to explain what the lim sup is and why all of that is coming down to this explanation or that one here. So essentially it means the lim sup is the largest accumulation point that your sequence has towards infinity. And maybe in this case it's just here, so this would be the lim sup. So this would at the same time be the supremum that you're talking about here. Okay, so now finally we have stability. So it means that after a certain point, your inverses exist. So no infinities up here anymore, and moreover even a uniform bound exists. So you can draw a line here that you never exceed for n bigger than n0. Inverses exist and do not blow up. Now, having this notion of stability, we should just shortly summarize the contents of our theorem 3 using these new words. Okay, so all we need here is that an converges uniformly to A, and then we have this equivalence. Okay, so let an go uniformly to A, then the following are equivalent. Number 1, A is invertible. Number 2, an is applicable to A. And number 3, or let me say 4, so it's consistent with the previous theorem, the sequence an is stable. And please realize that number 1 is only talking about A, number 4 is only talking about the sequence an and not about A, and only number 2 is talking about both of them. But if they're all saying the same thing, then that must mean that this uniform convergence gives you such a strong relationship between the operator and the approximating sequence that one is knowing all about the other. So maybe we've realized that we are being a bit sloppy now, so we are not mentioning the spaces x and y anymore, which of course you should do. And because during the proof of theorem 3 we have been using things like completeness and so on, so we should make the right assumptions at the right point. And to do so, let me go back to the very beginning of chapter 3. Okay, so at the beginning, when you're posing the problem, you say what is given and what is to be determined, then it's enough to take vector spaces. But then as soon as you come up with this strategy, you need some kind of convergence for elements in y, you need convergence for elements in x, so you need metrics, you need possibly a norm. So when you have a vector space with a norm, then you call it a normed space, of course. Okay, but then as we went on, we needed even more. Let's see where this happened. Okay, I think the first time we needed completeness was in this lemma 1, because we've been talking about Cauchy sequences and we wanted them to converge. Here we go. So for lemma 1a, we need completeness of that one space, which is x and y at the same time. And for lemma 1b, which is the general case of lemma 1, well, we are using A, so we are using the fact that, well, at least one of the two spaces, in this case, space x is complete. You could also factor A out to the other side and then repeat the argument. In that case, you would expect y to be complete. So it's for this lemma, it's actually enough for one of the two spaces x and y to be Banach spaces, so complete normed spaces, and then you can continue. But I mean, let's not fuss around. Let's say they are both Banach spaces. Right, but then lemma 1 enters pretty much all the rest, right? Let's see. Well, not lemma 2. Lemma 2 is fine without any other assumptions. So in lemma 2, all you need is inverses. That's not much, so it's enough to have vector spaces here. Okay, but then in theorem 3, we're not even talking about x and y, so we should be talking about x and y here. And here they have to be Banach spaces because we are using lemma 1. Right, okay, and that's exactly the same condition that you also need for your corollary 4, which is just summarizing theorem 3. Okay, so when you have uniform convergence, then everything is as nice as it can be. But remember that often you don't have that. So if we go back to the beginning of chapter 3, then we found out that typically you cannot expect to approximate your invertible operator A by a sequence of operators an that you can treat numerically, which usually means finite rank ones. Okay, you cannot do that. Only in some rare cases it's possible to deal with an not a finite rank, and then you can achieve uniform convergence. So we need this other kind of convergence, right? So I guess before we introduce that other kind of convergence and give it its own subsection, we should introduce a subsection for the discussion that we've done here. So sorry about that. Let me squeeze in the heading 3.1 here. And that is uniform operator convergence, because all the time here we're talking about uniform convergence. And this is of course essential to our arguments, especially in lemma 1 and all that follows from it. Okay, but now we're ready for section 3.2, and that is called strong operator convergence.